In OI, you often run into these geometry-related problems, and a lot of newbies are tripped up by them. So today we're going to go over some foundational principles that will make these problems a lot easier to solve. And then we're going to solve an actual problem based on these foundational principles that we just go over. Okay, so the two foundational principles. The first one is based on something that I assume you already know. Given any 2 points, you can calculate the slope of the line that runs through these 2 points with this formula: y2 minus y1 divided by x2 minus x1. So the slope is basically the change in y relative to the change in x. Okay, and so based on that, we have a principle here that says any 2 points on a line has the same slope. They must have the same slope. So that allows you to write down the formula for a line given any 2 points. So point A and point B are both given. So x1, y1 and x2, y2, they're given. And then, so any point on the line that runs through these 2 points, call it C, with x, y as coordinates, and x and y being variable, okay? And whatever that C is, as long as it's on that line AB that runs through AB, the fact is the slope of AC must be the same as the slope of AB. And the slope of AC is the left-hand side of this equation, is y minus y1 divided by x minus x1. And the right-hand side is basically the slope of AB, and they must be the same. And if you're anchored around BC instead of AC, then you get this second equation. So left-hand side is y minus y2 divided by x minus x2. And the right-hand side is, again, the slope of AB. So this is one of the most important rule. And it's kind of trivial if you know any geometry at all. What you don't know is how powerful that rule is and how useful that is when it comes to practical problem solving in OI. There's a corollary of that rule. It says the product of the slopes of two perpendicular lines must be -1. And if you think about it, so take a moment and think about it and try to understand why this is self-evident. The slope of any line, call it AB, is nothing but the change in y relative to the change in x. And then if a line is perpendicular to it, then you can see that the change in x relative to the change in y must be basically the same as the slope of AB, except that it's negative because the direction is different, because y would be increasing as you decrease x. Okay, and the second rule is based on Pythagoras theorem. It allows us to calculate the distance between any 2 points, in this case A and B. If A is x1, y1, and B is x2, y2, then the distance between A and B is this formula. And it's based on Pythagoras theorem because you consider a right angle triangle like this one, okay? And AB is just the hypotenuse, right? The length of the hypotenuse, we know based on Pythagoras theorem, is the sum of the squares of the two other sides, and then take the square root of the sum. Okay, so now that you're familiar with these two rules, which you already know, but you just didn't know that most of the time, all you need is those two rules. We're going to take a problem from the HKOI online judge and try to solve it and illustrate to you how these two foundational principles allow us to solve so many problems like that. So I'm going to put the link of this note file on the show notes. And so you can get to it. And then here you can click on the link and open up this problem. So take a moment and read the problem and train your comprehension skills first. Okay, so now you can resume the video and let's see that this problem is about Corona making some trips in the office. She's going to make N visits to N co-workers, and then she's going to pass the virus to anyone within a radius of D. So if you look at its sample input, it consists of the first row is N and D, okay? N is the number of visits she will have to make, and then we'll come back to D in a second. And the second row would be her starting coordinates. In this case, she will start at -2 and -1, and then followed by n more rows, each row representing the coordinates of one of those n coworkers that she will be visiting. The first visitor in this case is at 310. The second visitor is at 14.5. And as she make the trips, two trips in this case, she would be infecting everyone within a radius of D. In this case, D is 5. Okay, so let's look at a graphical representation of this case. Okay, so open a new window. Okay, so she starts at -2, -1, and then she will visit the first coworker at 310 and infecting everyone within a radius of 5. And you can see the pink area covers it. And then she makes a second visit to the second coworker at 14.5. And this whole pink area covers all the coworkers within a radius of 5 along this entire journey, which consists of 2 trips. Okay, so in this office is a very crowded office. As you can see, there's one coworker at every single grid point here, and your job is to count how many red dots will be infected along the entire journey that's within a radius of D. Okay, so to solve this problem, we first focus on subtask 1, okay? Because subtask 1 allows us to focus on a pretty small relevant area. It's a 400 by 400 relevant area. Why? Because all the coworkers are within a 200 by 200 grid, right? And then the D is less than 100. So all the infections would happen within a 200 by 200, 400 by 400 grid. And so that allows us to come up with a brute force solution in a 400 by 400 grid. Even if you consider every single grid point, that's only 160,000, right? Not that many. So for every one of those 160,000 grid points, you would calculate the distance, the geometric distance on that 2D plane from the journeys, all the trips, i.e. all the lines in the trips. And if one of those points are less than a distance of D from these trips, then you would include that point. And that's how you do the counting. Okay, so let's try to turn it into C++ code. Okay, so as usual in OI, we start with a template like that. You include the usual library, and then you use the namespace std to make everything simpler. First step is to declare the main variable that you would read as input in line 1, first line. And then you're going to read n more points. It's actually n plus 1 more points because the first row is going to be your starting coordinate. Always declare ij for convenience sake. And then you would read n plus 1 points. Okay, and to store n plus 1 points, you need to declare an array, right? And since n is at most 5 here, so we're going to declare 6 actually, because you have to also store your starting coordinates. And each point in a 2D plane consists of 2 integers. So a pair int is the perfect data type to store these points. So what we do here is okay, so now that we read the input, we're going to come up with the traveling, okay, the traveling logic. We're going to write a function called travel that does the job of traveling for each of those n trips. Okay, so in this travel function, we're going to do it brute force, i.e. we're going to consider every one of those points within the 400 by 400 grid. So in case you don't know, when you're watching a video like that, you should feel free to pause anytime and just pause it and try to digest what happened, slow it down to your own pace. This is the key to learning from YouTube, right? And if you don't know already, you should pause frequently and just don't let things slip by you because you don't have to. I won't be offended if you pause all the time. In fact, I would love it if I knew about it. Okay, so for every one of those points, you would calculate the distance of xy from line AB, the line segment AB. It's a line segment. So once you calculate that, well, let's declare distance. And then we're going to calculate later because we have to do some algebra before we know how to calculate it. We will check whether distance is less than d, right? If it is less than d, then we know we found an infection. So we would add that count by 1. And then we would print the total infected count at the end. Okay, is that the right way to do it? So hit pause for a second and think about whether there's any problem with this approach. Yes, there's some problem with this, right? Because for every trip, we're going to be considering all these points all over again. And so for all these points, we're considering them many, many times. And there's a risk that we are double counting the infection. We may be counting that particular point as an infected point over and over again. So the right way to do it is to not just keep track of the count. You have to kind of keep a database of all these infected coordinates that you found. And then you want to kind of only keep track of the unique infections and eliminate the duplicates. And in C++, the best way to keep a database of unique elements is to use set. I mean, you can use unordered set too, but set is good enough for most cases. So I like to just declare set. And it's going to be a set of 2D points. So it's going to be a set of pairs. And then let's call it infected. Okay, so every time instead of adding 1 to the infected count, you would add that very point that you find infected to the database, like that. And so in the end, you just print the size of that set. That's the answer. So that's the main logic. Okay, so we've gone a long way in this solution because this solution has everything except for the calculation of the distance of xy to the line segment AB. And so that's all we need to do. And so now let's go do some algebra. Okay. How do we figure out, in this case, the line segment being AB and x1, y1, x2, y2 are given, and then we're considering every single grid point and take any particular grid point xy, which is also given, by the way, because you're looping all these values of xy in the 2D loop. So point E, you want to calculate the distance between point E to the line segment AB. How do we do that? Well, before we do that, for convenience sake, we want to let delta x be the change in x coordinates, x2 minus x1, and then delta y is y2 minus y1. Okay, so delta x is basically this horizontal distance, and delta y is the vertical distance here. And then we're going to choose to, so point C is very important here. Okay, point C is the nearest point to E from the line segment AB. And one thing you would necessarily know is that EC must be perpendicular to AB, right? For C to be the closest point, line EC must be perpendicular to AB. And the way so we just want to calculate C. If we figure out what C is, then the distance of CE is just Pythagoras theorem, right? Remember the second rule that we talked about being the foundational rule. But how do we calculate C? Well, we know C is not, it cannot be any point. It has to be on line segment AB. So we can represent it parametrically using T as the variable. And so you can represent C as x1 plus T times delta x, and then y1 plus T times delta y. And for a moment, just think when T is 0, C is basically at A, right? This is x1 and this is y1. And when t is 1, remember delta x is x2 minus x1. So doing some algebra, you would know that c would become x2 and y2, which means that c is exactly at b when t is 1. And then when t is 0.5, it will be right in the middle between a and b. So as you dial t from 0 to 1, you would move a from a to b. Okay, so this is a very convenient representation of C because we boil it down to only one unknown, T. And we just got to figure out, work out what T is, solve for T. Once you solve for T, then everything else just follows naturally. Okay, we know that EC is perpendicular to AB. And so we can use the rule number 1 to calculate the slope of EC here. And that's the expression, right? And then slope of AB is basically delta y divided by delta x. And so they must multiply to -1. So write down the formula here. And you can do some algebra, cross multiply the numerator with the denominator. And so you turn it into this formula. And then you group the t together and then simplify it. And then you can solve for t. And so everything on the right-hand side are given values. You already know what they are. And with that formula, you can solve for t. And once you solve for t, then you can figure out exactly what c is. Once you know what c is, then you can calculate EC, which by Pythagoras' theorem is this formula, the square root of EC. And so your job is for every single point xy, you calculate EC using this formula and check if this number is less than or equal to D. If it is, then you know this point is infected. Okay, let's write a C++. Let's express these ideas into C++. Okay, so to do that, the first step is it's really convenient to calculate dx, right? So dx is x2 minus x1. Well, but we don't have x1, x2 yet, so let's just write down x1 is a dot first, and x2 is a dot second. No, x2 is not a dot second. y1 is a dot second, and then x2 is b dot first. y2 is b dot second. Okay, so with that, you can calculate delta x, and then you can also calculate delta y. Okay, and so are we ready to calculate distance? To calculate distance, we first need to calculate t, right? Remember, first calculate t, and then you can calculate EC. Okay, so t is this formula, right? So t is dx times dx times x minus x1. Yep. Plus c times that, and plus dy times y minus y1. Okay, and then the numerator is the delta x squared plus delta y squared. So we're going to divide it by dx times dx plus dy times dy. Well, we got to be careful because both the numerator and denominators are integers, but we really want non-integer we want floating point divisions. So we want to multiply that by 1.0 to turn that into floating point. So that's t. And once we have t, well, we want to be careful with t too, because as you know, t is down from 0 to 1. And even if the point E is right here, you don't want to calculate the distance from E to this hypothetical C point, because corona only travel from A to B. The infection only happened along this line. At no point the infection was starting from this imaginary point. She was never there. So the distance from E to that point that's perpendicular to AB is irrelevant. The real distance that matters is the distance between E and A. Okay, so that's what you want to calculate. So you just want to guarantee that t is always within 0 and 1. You don't want t to be negative. You don't want t to be larger than 1 over there, no matter what e is. And so what you want to do here is to clip the values of t between 0 and 1, like that. And now you're really ready to calculate distance, right? But to calculate distance, the formula of distance is reasonably complex and it involves a square. So it kind of helps to have some temporary variables called left-hand side. Left-hand side is going to be this part, x minus x1 minus t. So x minus x1 minus t times dx. And then you want to take square of it, right? So LHX just that would give you the square and store that back into LSX. And the right-hand side would be the same. And so distance is just the square root of the sum of LHS and RHS. Well, square root is a function that you can only use if you include the math library, math.h library. Okay, so I think we're done with the solution for at least subtask 1. Let's test it. Take it for a spin in this problem. Okay, and let's see. Well, looking good. And so if I submit it, voila, solves for subtask 1. Good, very good. Okay, but there's a problem with this. Even though the test data didn't challenge our solution, but our solution has a fundamental flaw that usually needs to be fixed. There's some floating point imprecision as soon as you perform any division here. And so starting from t, everything that follows it will be imprecise because floating point is never 100% precise. And in OI, a lot of times you're required to have answers that are absolutely precise. You're not supposed to have any imprecision. And that means you want to retain all the computation in integers as much as possible because in integers, you have absolutely perfect precision. Okay, so we're going to fine tune this solution to make it to eliminate all the floating point imprecision. And so to do that, we're going to create a V2 file. Okay, we'll copy and paste most of it and see how we can come up with a better version of it. Okay, we first need to do some algebra, right? Okay, so to get absolute precision, the imprecision happens here when we do a division. Whenever we do division, there will be imprecision. Here, when we do square root, when we calculate the final answer for EC, square root also introduces imprecision. So we have to fix those two issues. Okay, but to begin with, we want to, for convenience sake, we want to let delta x1 be x minus x1. Because as you see, x minus x1 shows up quite a bit, twice here at least. So that allows us to simplify our arithmetic, our algebra. It's also convenient to let L equals to the delta x squared plus delta y squared. You can see it also shows up here. Okay, and so you can rewrite t into something simpler using delta x1 as the new notation. And if you multiply both sides by L, you get to t prime, which is the integer version of t, and the numerator of this expression would be an integer. So now by considering t prime, which is t times L, you eliminate the division here, the precision that comes with it. Now, let's look at EC square. If you just consider EC square, then you end up without the square root, and that also eliminates the imprecision. And then, but here you still have t, right? T is a floating point number. We kind of want to turn t into t prime, which we know is an integer. And the way to do that is to multiply both sides by L square. And so because this is a square, you would put the L inside of both left-hand side and right-hand side of the squares. And this becomes L times delta x1. And this, because TL is t prime, so this becomes t prime. And this is also t prime. Both are integers, right? So this is an integer expression. And now that you have an integer expression, instead of comparing EC and checking if it's less than D, you would compare this expression and see if it's less than D squared L squared. And that's how you eliminate all the floating point imprecision. Okay, translate that into C++ language. You would first, let's calculate L, right? Because this L expression here that would make everything more convenient. Okay, so L is dx plus times dx plus dy times dy. And here, instead of calculating t, you would calculate t prime. But before t prime, as you saw, for convenience 6, you would do dx1 being x minus x1, and then dy1 being y minus y1. And so now instead of doing t, you calculate t prime. And in t prime, you eliminated the division. And then this is dx1, this is dy1. You can actually eliminate all the parentheses. You don't have to, but I just kind of like to keep it clean. And you also still need to clip t prime between 0 and so instead of 1.0, it's L, right? Because you're multiplying both sides by L. Okay, so it's complaining a little bit here. And because we want to declare TP as integer, okay? And then TP and L. Okay, good. So now it's not complaining. Okay, now the left-hand side and the right-hand side. We want that to be, so x minus x1, as you know, is dx1, right? And then you want to multiply that by L. Okay, and then this is TP. So we multiply both sides by L. This is dy1 times L, and then TP. And then distance, so we no longer do square root. Just add them up. And then you want to see if it's less than D squared L squared. So D plus L times L. Okay, so I think that's the right code. And I'm curious if this would pass subtask 1, 2. A lot of times we just make careless mistakes and then we'll do some debugging. Okay, so we did make some careless mistakes. What would that be? And dx. Okay, so let's look at the formula. And you're supposed to check EC squared times L squared is less than or equal to D squared L squared. Oh, okay. So I think here I'm just carelessly putting a plus sign instead of the multiply sign. Okay, so this is the code I'm going to submit, and good. And I'm going to submit it. As I expected, it doesn't pass. You can know there's still some issue here. When you're doing so much multiply and then L times D times D, this number gets very large. And so, oh, and there's also integer here. We want all these to be integers, okay? But the problem is still there. The problem is when you're doing so much multiplication, the number distance becomes very large and it overflows the limit of an 32-bit integers. And so what you want to do is to turn, instead of just changing everything into long, you can just do this. So every int now is long, and it's complaining because this 0 literal is a int, not a long. So you want to force that into a long literal. And if you compile this v2, well, you want standard C++11. It's still complaining because it expects the prototype of the main function to be a 32-bit int, not a long. But now this define statement turns that into long also, and that's no good for the compiler. So you want to kind of force this to be a 32-bit integer so that it can compile. And now that everything is long, we're gonna submit it again. and see if it passes. Voila, perfect. Okay, so we solved this problem using algebra, right? It's a little bit of algebra, but it's not extremely complicated. And all we use is the two cardinal rule. One is the Pythagoras theorem that allows us to calculate the distance of 2 points. And then the other is to invoke the, the slope idea that these two lines must be perpendicular. So the product of the slopes must be -1. Okay, but this whole problem, it's actually a lot easier to solve if you use vector arithmetic. Okay, so if you see AB as a vector, call it U, and then AE being another vector, then the distance, i.e. the length of EC, is the cross product of U and V divided by the length of U vector, like in this formula. And we take the absolute values because the cross products comes with a sign, i.e. if E is on the other side of the vector U, then the cross product would give us a negative number. But here we're just concerned with the absolute distance between E and C, no matter which side is on. So we can take the absolute value and not worry about the sign. So that's the formula. So you think, oh, this is so simple, just take the cross product. But it's not just that. There are some hairy situations. For example, if E is here, then then you don't really want to consider the projection point C and the distance of C to E because the infection never really started from C. The whole traveling start from A and get to B, it always remained within AB. At no point was there any infection starting from point C. So what you really want to consider is really EA here, and you want to check if this vector is less than D. And when does it happen? This happens when the dot product of the two vectors are negative. So think about why, right? Dot product gives you the projection of one vector on the other. And when E is over there, the theta is larger than 90 degrees, and the projection is on the other side. It's going to be negative. Okay, so, you can also think of this cosine theta. When theta is larger than 90 degrees, cosine theta is negative. So you want to check if the dot product is negative. If it is, then you want to just use the distance V as the point of comparison. Also, when the point is all the way out there on the far end of B, and so in that case, the projection is also outside of the the B end. And in that case, you really ought to consider the distance BF instead of the projection onto the vector U. And this happens whenever the dot product is longer than vector U. Again, the dot product is the projection, right? Cosine theta. Okay, so now let's turn these vector arithmetic into C++ language and solve this problem in the other way and see if it's much easier. Well, we have to introduce or make sure you acquire the knowledge of struct. We solve these problems using pairs of int, and that's usually enough. But when you're dealing with vector, you really want to use struct here. And struct allows us to have a lot more flexibility in declaring custom data type. In this case, it's still just two numbers, two integers, because we're dealing with a 2D plane. And once you declare a struct like that, then you can declare a point A like this, and you can set a dot x to be 3 and a dot y to be 5. And then you can print it out and see what happens. Point, and it would print out the A's coordinates. And you can declare point B, and you can set that to -10 and 5. It would do the same thing. In fact, let's do that. Let's do 3 and 5. Okay, let's see if you print the same thing. Okay, so that's another way to initialize a point, a struct like that. You can just do it all together. Point A and bracket 3 and 5. That should give you the same thing too. Okay, now you're using C++11 notation, so we want to add the compiler flags. Same thing. Okay, so that's point. And we're going to use that to help us keep track of all the points to visit all the coworkers. Now, to do vector arithmetic, we need to learn a few more things about struct. So a vector is essentially also two integers, right? So it's no different from a point. But we want to do vector arithmetic. And in C++, it allows us to have built-in struct functions like that. So, because very often, okay, let's just comment this out first. And if you declare vector u, and let's put some values in here, and vector v, and if you want to add, so vector w equals to u plus v, okay, it doesn't let you compile it because you can't add two vectors. But so often you want to add vectors, subtract vectors, and then later on we're going to do dot product and cross product. And so we really want to have the power to do that. And C++ allow us to overload operators so that you can add vector. So the way to declare it is because the addition operation returns another vector. So this is the return type. And then we're going to overload the plus operator. And then one vector will be added to another. And what we return is basically the sum of the x and the sum of the y for the addition operation. And so once you do that, then you can perform this addition easily. Okay, so let's see. -7 and 9. That's what you expect, right? Good. Okay, so now we're going to overload the minus operator too, because it's pretty commonly used. Okay, so that is also going to be pretty simple. Okay, so other than that, we're going to do dot product. Dot product returns an integer, and it would add one vector with another vector. And what it returns is x times t dot x plus y times t dot y. And cross product, if you remember the formula from geometry class, is x times t dot y minus y times t dot x. Is that correct? Yep. Another function that's usually pretty useful is magnitude. And it's going to be double because we're going to have to take the square root. It would return the magnitude of this vector based on x and y values, and square root of x times x plus y times y. The length of the vector, basically. Okay, so we have this whole vector struct built in, and then we're going to be able to use it. Okay, we're going to copy that. So first, let's just create a file called v3. Okay, and then we're going to copy the vector implementation here into v3 so we can use it. We'll put that on top. Okay, the main body doesn't need to change, but now that I have vector, I'd like to declare these points as vector instead, even though they're really points, right? They're not vector, but you can kind of roughly use it the same way because we're just trying to save two numbers, x and y coordinates. And the rest doesn't need to be changed. And so you read those points. Oh, now that we're using struct, so it's no longer dot first, dot second, it's dot x and dot y. Clearer names, right? Dot x, dot y is definitely better than dot first, dot second. And then when you travel, you're traveling. So we need to redeclare A and B to be vector. They're really point again. Vector is kind of a misnomer, but I'm too lazy to type def into point here. Okay, so we're going to travel from A to B. And when you travel from A to B, we're still going to brute force it. Let's um, delete all of it. We don't really want to be encumbered by the previous code. Okay, so int is still going to be double. Okay, we're going to kind of ignore the imprecision problem for now. And then we're going to check if distance is less than d, less than or equal to d. Okay, so how do we calculate the distance again? Okay, so let's look at the diagram here. We want to calculate the cross product between u and v first. Okay, so how do we get u? U is b minus a. Okay, so vector u is b minus a. So isn't it nice that we overloaded the minus operator? We can just do that. Okay, so that's u. And what about v? V is e minus a, right? E minus a. What is e? E is x, y. So as we loop through different values of x and y, we want to set up e as well. And that's just x and y here. Okay, now we have u and v. And then we're ready to calculate the distance. Distance is cross product u cross v divided by the magnitude of u. And we want to take the absolute value of it. Okay, but we don't want this formula all the time, right? If it's here, then we don't want this formula. If it's there, we don't want to use that formula. So we first want to check if u dot v is less than 0. If it's less than 0, then we are just going to calculate the magnitude of v. And if u dot v is, let's see, u dot v is larger than u times u. Okay, so it's larger than u dot magnitude times u dot magnitude. Then what's else if here? Then it's FB, right? So basically, or EB in this case, the distance. So it's E minus B, and then you take the magnitude, the length of this vector. And if it's not neither case, then you use the main formula, the cross product. And then you check if distance is less than D, and then you insert it if it's infected. So I think that's what we want to do. Okay, let's test it. Hopefully it still passes the task 1. Looking good. Well, perfect. Okay, so it passes. A few improvement I want to make here, because it doesn't really depend on x and y. So you can take it out here and just avoid recalculating that all over again every time. And then you can also declare distance outside. It doesn't make much difference, but these are the minor improvements we can make. Okay, that's the vector version. And one more time, if you want to eliminate imprecision, then I'll let you figure out how to improve upon this version and eliminate the floating point imprecision here. So now we have this order of R squared solution for subtask 1. R squared as in, because we're scanning every single grid points on the relevant area, and the R in subtask 1 is pretty small, it's 100. And so we can just scan every single grid point on a 2D plane and still finish within 1 second. But this R squared solution is really not good enough for the full solution, because in the full problem, the R is up to 10,000. And so you really need an order of N or order of R solution, a linear solution to get full score. And so if you look at this problem, scanning every grid point is not good enough. And so instead of that, what you do is to turn it from a 2D scan into a linear scan. And that's often the correct approach for a lot of these computational geometry problem. You turn a 2D scan into a 1D scan, and then you can have a order of N solution or order of R solution in this case. And now, in this problem, in this trip from A to B, the entire infected area is shaded pink here. And it's just the overlap of two circles, this circle around with the center A, and this circle with the center B, as well as a rectangle. Okay, and you can see there are overlaps here. But if you can scan every X coordinate and then figure out the lower bound and the upper bound of the intercepts, then you would have a linear solution, right? And you can do some algebra to figure out what's the lower intercept and what's the upper intercept. Okay, so for now, let's focus on the circles. Okay, so this circle that's centered around A, we can use Pythagoras theorem. So for every X, you can calculate the lower intercept and the upper intercept. In this case, it's y top on the top and then y bottom at the bottom. And AE is really just the radius, as well as AF. They're both radius. And radius is D in this case, as given in the input. Okay, so using Pythagoras theorem, you can say, okay, AE is D. So you can calculate. So x minus x1 squared plus y top minus y1 squared is D squared. That's saying that AE equals to D. And so you can rearrange the algebra equation and calculate y top. Remember, all these numbers are given, right? For every x, and these are constants. For every x, you can solve for y top, the upper intercept. You can do the same thing for the bottom, for the lower intercept. So for every x, you can figure out the lower intercept and the upper intercept, i.e. the entire range of y of all the grid points that are infected. And then you can do the same for the other circle. So now you finish the two circles, and then you can move on to the rectangle. The rectangle is a little bit harder, and don't worry, I'm going to walk you through it. So let's start with this question. Okay, so take any vertical line. Okay, what's the lower intercept, y bottom, and the upper intercept, y top? And we'll need to do some algebra to figure it out, but it's not entirely impossible to figure out. So given x, we need to calculate the y first. Y being, so C is xy is the y coordinate given that x that lies along the line AB. We've done it before, right? So first, let's simplify this by letting delta x be the change in x, and then delta y being basically this vertical line. Okay, and so based on the principle number one we talked about earlier, we can deduce that the line AC has the same slope as line AB. And so that allows us to work backward and get y given the x. Okay, so this is y. But y is not enough, right? What we really want is to calculate the, so let's go back. We want to calculate the y bottom and y top. But y is a good starting point because y plus this EC is y top, and y minus the CF is y bottom. So what is CE and CF here? Well, can you see these two red triangles? They are equivalent triangle, as in this angle is the same as this angle. And so you can write down this equation. So take a moment, hit pause if you need to, and try to kind of prove to yourself that these two are equivalent triangle. Okay, so now EC divided by D. So this hypotenuse divided by this side of the right angle triangle has the same relationship as AB versus the delta X here. Okay, so we wrote down this formula. And D is known. AB is kind of known because you know both A and B, so you can always calculate the distance. In fact, we calculated that earlier in the version number 1 in the subtask 1 solution. And then delta X is also known. And so that allows us to calculate EC. And that's great because EC is exactly what we need, is the offset we need to get to Y bottom and to get to Y top and Y bottom. And so this is Y top, and this is the formula for Y bottom. And with that, you would think we're done, but not yet. There's something really tricky about this problem. It's what if the vertical line is here? And you can see this vertical line, while on the top, it crosses this line also. So the calculation for Y top for this X is the same. It's this formula, Y plus EC. But the Y bottom is not exactly the same as F in this case. It's not exactly this formula because it actually hits this line first before the bottom hits this line, right? So this line is a real intercept. And so we can't really use the same formula as for this line, ECF. Well, if you draw this line, you can see this line is perpendicular to the line AB. And so the slope is going to be the inverse times -1. So it's delta X divided by delta Y and the negative of it. And you can quickly see this is the correct formula for this line that this vertical line is intercepting. And what is this line? This line gives you the ability, so you can calculate, given the X, you can calculate the Y. And this Y is the real intercept on the bottom end instead of the Y bottom. So you use this, and then you use, so when the vertical line is here, you know that the top is clipped by this formula instead. And these two formula will give you another possible lower bound. And basically for the lower bound, you take the minimum of Y bottom, and you take the maximums. You take the maximum of the Y bottom formula as well as what this formula gives you. And then for the upper bound, you take the minimum of this Y top formula as well as what this line formula gives you. And then also don't forget, if the slope of AB is negative, this is a case when AB is negative, when the slope of AB is positive. But when the slope of AB is negative, then you kind of have to flip this the other way around. So think about how that's different when the slope of AB is negative, and then you have to adjust the formula accordingly. Okay, and finally, I'll give you one more tip. And this tip is very commonly applicable and super useful in many OI problems, not just in computer geometry, is that you really want to make sure that x1 is less than or equal to x2. So you want to make sure point A is to the left of point B. Because if it's not, then you have to write code that's twice as complex. But if you guarantee that first, if you make sure x1 is less than or equal to x2, then everything is much simpler by a factor of 2. Well, then what if x1 is larger than x2? Well, then you can just swap those 2 points. It wouldn't hurt because whether you're traveling from B to A or A to B, the infected area is the same and the math is the same. But by making sure that you're always traveling from left to right, you make the logic of the code much, much simpler by a factor of 2. And then so in the end, when you put it all together, then after all the scans, you scan for every single x, find the lower bound, upper bound for all n trips, which is up to 5. You'll end up with a list of ranges, the y ranges, that may or may not overlap. And so what you need to do is to merge any overlapping ranges for each x, and then count how many discrete integers lie within that range. And when you do that, once you finish doing that, then you have built an order of R solution. And even for R equals to 10,000, like this problem, your code will churn out the answer within 1 second.